So if this one is does not contain iron, so it's ferrous and non-ferrous. And from this ferrous alloy, okay, based on the range of the composition, we further classify it. We have steel for the carbon content below 2%, and in between 2 and 4, we have what we call cast iron, which we have discussed last week. Cast iron, very short, but content. So, but the cast iron, if you still remember, we have four types, right? The white cast iron, the gray cast iron, malleable ductile cast iron. Okay, so we have four types of cast iron. And for steel, we have not defined it yet. And today we will divide all this, we will classify all this steel into two parts. Okay, so one is the plain carbon steel, another is alloy steel. So what is meant by plain carbon steel? Well, basically it's this is the alloy containing, of course, we are talking about ferrous alloy, so Fe, and only carbon. Okay, it might have some very small amount or small impurities inside the alloy, but it's very insignificant amount. So intentionally, we just alloy the iron with carbon only. Okay, and on the other hand, we have the alloy steel, which we alloy it not only by carbon but with other metals. Okay, so we have plain carbon steel and alloy steel. Okay, so all right. Mhm. So this is bit recap. So the plain carbon steel is an alloy of steel where carbon is the fundamental constituent and no base of other alloying element is specified. So this is what I mentioned just now. So plain carbon steel, we only intentionally we add the carbon. It might have some impurities, but that is not what we or the amount is so insignificant. Okay? So some limitations of plain carbon steel include cannot be strengthened beyond 690 megapascal. So it has some limitation because we only restrict the alloying element to the carbon, and we have the restriction of percentage as well. I mean, we cannot exceed 2%. Otherwise, it will not be called as steel anymore. So we have the restriction of alloying element as well as we have the restriction of content or the percentage composition of the carbon. So the the so this result in the limitation of our strengthening mechanism, and we cannot go beyond 690 without losing the ductility and impact resistance. Okay, and also the plain carbon steel is not deep hardenable. It is hard. It has some amount of hardenability, but due to the uh, absence of other alloying elements, so it is also limited. Okay, the hardenability, and of course, we know that iron is very susceptible to corrosion. So without any alloying element, there is no protective mechanism. And for the plain carbon steel, And we will see on the other hand what the alloy, the alloy steel offers, how it um, improve, or it how there is a mechanism to improve the corrosion resistance. Okay, but for the plain carbon steel, only you have the iron and carbon, so it has low corrosion resistance. Okay, so this is almost the same as oxidation, because corrosion is about oxidation of iron and so on, right? And they have a poor impact resistance at low temperature. So this is related to ductile to brittle transformation, because we know iron is it will have this ductile to brittle due to the crystal structure of BCC. Okay, ductile to brittle due to BCC. Right. So this is the plain carbon steel, okay, and the alloy steel. So we we can actually from here, okay, from here we could actually divide that or classify it, okay, uh, depending on the carbon content, So we will see in the following slides, okay, how much is the carbon content. And basically it is classified into three categories: the low carbon steel, the medium carbon steel, and the high carbon steel. And if this in this range, okay, in this range, say 0.25 and 0.25 to 0.6 and 0.7, 0.6 to 1.4. Okay, we will later on we will not note this here, but what I am trying to introduce here is that from the steel, we could classify it into three categories based on the carbon content, and if the alloying element does not involve any other metal except the carbon, okay, so we will get what we call as plain low carbon steel, plain medium, or plain just carbon. Okay, so and apart from this plain steel, okay, plain carbon steel, if we add some element, it will result in different class or different category of steel. This is the what is traditionally acknowledged. This category, this category of steel. Okay, so today we will look at all these categories except for stainless steel, well, which we will have that explanation on the other, maybe next Wednesday. Yeah. So because stainless steel is a bit special, because it is widely used and it can further be categorized. So today, briefly, we will have a look on all these groups, all these category of steel. All right. So the learning outcome for today, okay, just so that we are clear what we are going to put ourselves into today is we want to be able to determine the advantage of using alloy steel and compared to plain carbon steel. So we want to compare these two. Okay, that is uh, our first target for today, and we want to be able to explain the effect of various alloying elements. So different alloying element gives different effect. So we want to be able to understand that. And at the end of the session, we will get ourselves into this what we call as maraging steel. Well, basically is martensite plus we age or we apply aging to the material. So maraging steel. So that is our three target today, objective today. So let's get ourselves into this. So the first steel that we are looking at is the plain carbon steel. Okay, this one, plain carbon steel. Okay, plain low carbon steel. So plain low carbon steel contain less than 0.5 weight percent carbon and cannot form martensite. Okay, so right here is less than 0.25% weight percent. Okay, so it cannot form martensite. Why? Because the carbon is too little. Okay, so if you still remember how the martensite is formed, basically we have this steel, or well, steel consists of ferrite or iron and also carbon. And when we heat it up above two above 7 to 7 degrees Celsius, it will transform itself into austenite. Okay, it will transform itself into austenite. So the austenized steel, it has FCC structure, and the carbon dissolved into the crystal structure of iron. Okay, into the crystal structure of iron. The carbon dissolved inside, dissolved inside. So when it cools, when it cool down, when we remove the heat source, and it cools down, the temperature drops, and it go beyond the eutectoid temperature. So from the FCC, it will try to change to BCC, but due to the rapid cooling, due to the rapid cooling, okay, due to the rapid cooling, the carbon didn't have or don't have that opportunity to diffuse out. Okay, for slow cooling or moderate cooling, the carbon, it has the time and also have this opportunity to diffuse because there is heat, so there is it can still diffuse. But if we so it will form the perlite, the perlite, the I mean the cementite, lamella, cementite of and ferrite in lamella, alternating lamella structure, slow cooling and moderate cooling. Okay, but for the fast cooling, the carbon is trapped inside, and suddenly the temperature is abruptly dropped, and the carbon did not or do not have that opportunity to diffuse out of the crystal structure, and the door is closed, and the heat is removed, so cannot move anymore, cannot diffuse anymore. So it's trapped inside. Instead of the ferrite transforming into the BCC structure, it becomes BCT structure due to the distortion, okay? Due to the presence of carbon. But for low carbon steel, the amount of carbon is so little, it cannot form martensite. It cannot form martensite. And if we do the slow cooling, right? So plain low carbon steel, 1 point is the amount of carbon. Okay. Key point number 2, cannot form martensite. Okay. Key point number 2, cannot form martensite. And of course, if we cannot form martensite, we don't have any alloying element to create precipitate. So the only last resort to to strengthen is by pole working. Okay, pole working means that we do rolling or drawing, all this, we impose this deformation to increase the strength by higher density of dislocation or strain hardening. Okay, uh, so even if we do expose this material to slow cooling rate, so we let it, we don't try to insist of reducing the smarter side. We cool it off at moderate or slow cooling rate. The amount of perlite is very little compared to the cold microstructure, where it consists mostly ferrite. Yeah, amount the carbon itself is too little. Okay, this dark color, this dark phase, is the perlite. Okay, if you zoom in more, if you zoom in, maybe you see by SEM, or you will definitely see this lamellar structure. Okay, so we are bit, the magnification is bit low, so a bit low. So yeah, we could only see the ferrite and the perlite, and the perlite is too little, is in small quantity compared to the whole microstructure. Okay, so that is plain carbon steel, plain low carbon steel, right? And because of we, you know, it's always if you have high strength, if you have straight, if you have this kind of like precipitate hardening or martensite, definitely the ductility will be low. But if you don't have that, so we could safely say that the plain low carbon steel, it has very good ductility and toughness. Okay, it can be shaped easily. It can be covered easily, because of the high ductility. It is machinable, weldable, and it also, because we don't use any alloying element, of course, it is not expensive. And due to this ductility, we use this plain low carbon steel in the car body. Why? Because ductile material, it absorb the impact energy. Yeah? When you have collision, when you have when you crash, you know, this ductile material, it will give you, if it will deform first, it will deform, and this deformation actually, it needs the energy, so it absorbs this energy from the impact, so the passenger will be safe, right? So that is why we use the uh, plain low carbon steel. Okay, so we want to reduce the impact on the passenger, right? So that is one of the example of the application of plain low carbon steel. And on the other hand, we have uh, HSLA, the high strength low alloy steel. Okay, so this is done. Okay, so we go to the high strength low alloy steel. Okay, HSLA. It contains other alloying elements such as copper, vanadium, nickel, moly. and combined concentration as high as 10 weight percent. So you add up all these four. Okay, you add up. This is for example lah. For example, suggest. For example, we could have other element, and you add up this alloying element, and it goes around 10% of weight. Yeah. So they have higher strength and hardness than plain low carbon steel due to the addition of these alloying elements. So it is very understandable. You have more alloying element. You have the same amount of carbon content, but you have more alloying element. So you have more distortion of the plane, because we if we recall back the how this allowing mechanism, we have a big and small one. We have the substitutional and interstitial. So once it is it has a different size from the host atom, so it create compressed if it is a in larger size, so it will create this uh, force in tensile. Okay, in tensile, or surrounding will experience the compression lah. But it itself it in tensile, but if it is smaller, then the surrounding will get or experience the tensile. Okay? So anyway, the more the alloying element, the higher the strength, right? So it has higher strength, higher hardness compared to plain low carbon steel. And this steel can be heat treated. So when we say heat treated, when we relate to heat treatment, automatically we have to relate with either, heat treatment means we use the heat to alter the microstructure, or we use the heat, of course, when the microstructure change, the properties also change. So just by manipulating the heat, we alter the material. So that is what meant by heat treatment. Okay, so when we say in steel, when we say it is heat treatable, automatically whether we can form it the martensite, or other like finer perlite, or all these sort of things. And number two is the precipitate. I hope you still remember the precipitation hardening. For example, if we have um, uh, a phase, okay, let's see here. Okay, so this is very basic of precipitation, example of precipitation hardening. So you have this all this iron, the ferrite matrix, and we have this small precipitate, fine precipitate. Okay, so it is not this precipitate is actually in 3D lah. Okay, not the surface only. Inside we have this kind of precipitate. Okay, so this precipitate uh, uh, okay, it strengthen the material because it hinder the dislocation movement. Okay, so this is back to, I think, module 4, right? So how it is formed, okay, we discussed this quite a few times already, but I just want to refresh back or revise back we have two metal. We have two metal, metal 1, metal 2. Okay, so metal 2 we add in and we heat up or we melt it together. So it will dissolve in metal 1 matrix until it exceed the solubility limit. Okay, after it cannot dissolve inside the crystal structure of metal 1, then it will form another phase. Okay, another phase. So precipitation hardening, we just add not much, okay, not much this M2 metal 2. So it will form a small particle. Okay, we don't want very big one. We don't want, to compete with the matrix itself. Okay, so is if you have alloying element which atau or the alloying atom, uh, how to say, uh, when we do alloying, at first you have the metal matrix or the host metal, right? So you add the alloying element. As long as the alloying element still dissolve into the host metal matrix, okay, host metal matrix. So it it will harden the material uh, by the mode of solid solution, so it dissolve, become solid solution, whether it is substitutional or interstitial. Okay, but if the solubility limit is exceeded, it goes beyond, okay, the composition of the alloying element exceeded this matrix solubility. So the matrix, the crystal structure, the, the crystal, it cannot accommodate more alloying element. So this uh, addition or this excess of alloying element, it will form another phase. Okay, another phase, that is the small precipitate. Okay, small precipitate. And another phase, by saying another phase, means the composition is not the same as the matrix. Okay, this here, if you do analysis here and here, it will not be the same, not be the same. Okay, so HSLA, okay, HSLA, sorry for very long elaboration on this. So HSLA, we have, apart from carbon, we have other elements added, and this element can help to produce this precipitate. So that is why we say it is heat treatable, because low carbon steel cannot form martensite, obviously, right? But it can produce the precipitate, so it is heat treatable. All right. So among the application, we use it in pipelines. Okay, in pipelines, among the application, we use it in pipelines because well, if it has sufficient strength. Okay, it has sufficient strength because we add the alloying element is little, alloying element. So if we add this alloying element and the strength is improved greatly, so we have higher ratio of strength to weight. So means that we have light material but very strong. Okay, so it's good, huh? Right? And it is ductile, formidable, and machinable, yes, because it has low carbon. And Okay, compared to the low carbon steel, the plain low carbon steel, it is resistant to corrosion. So this is one of the key properties of the HSLA, right? So that's why we can use as in pipelines. And all right, so that is about the HSLA, and then low alloy, and then we go to the medium carbon steel. Um, okay. Plain medium carbon steel, it has the percentage of 0.25 to zero point 0.6. Okay, 5 HSLA. So sorry, this is combined high strength low alloy, right? Plain and HSLA, and then we have 0.25 to zero point 0.6. We classify it as medium carbon steel, and yeah, of course, we have this plain medium carbon steel, and how does it looks like. So this alloy may be heat treatable by austenizing, punching, and then tempering. So it means that it can form the martensite lah. And why it is say maybe, so because we have a range of carbon. Okay, we have a range of carbon. If it is on the lower end, it might not be heat treatable, right? So if it's actually it's exceed zero point 0.3, it can be heat treatable. Okay. Uh, okay. This alloy may be heat treated by austenizing. I think we are clear on this heat treatment of producing martensite, right? So we just increase the temperature, and then we do fast cooling or quenching, whether quenching in water or oil, So fast cooling, and then just to improve the ductility a bit, then we temper, right? So this plain medium carbon steel have low hardenabilities. Okay, so it means that it is possible to form the martensite, but the carbon content is still low. Okay, the carbon content is still low, so only the area near to the surface they can be hardenable. Okay, so I think I hope you guys still remember the hardenability. We do the test also, like we have a bar, and then we increase or we hit the bar above the electric temperature, so it changed to austenite, or the process itself we call this austenizing. Okay, we austenize the steel bar, and then we quench the one end of the bar. So one end it experience fast cooling, so it transformed to martensite. And because the martensite is, or the carbon is big, it's little. Okay, it's little. So hardenability, you check the hardness along along this one, and then you check the hardness, and then you get how deep it can be hardened. Okay, how deep it can be hardened. So that is hardenability. So for this medium carbon steel, we mentioned that the carbon is limited. Okay, so the hardenability will be low. Means that uh, the depth is not much. The depth is not much. The hardenable depth is not much. Okay, the addition, okay, that is plain for the plain one. Okay, so if we add chromium, nickel, moly, we can improve the capacity of it to be heat treated. And of course, like the low carbon steel, we can also improve the strength of the material. And well, it's good, wear resistant is understandable because the, 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 the surface is hard. Okay, the surface is hard, so hard material, it has good wear resistant. And this is how it looks like for the medium carbon steel. So if we quench the plain one, you get this martensite formation. Martensite means this needle shape. This needle shape, all the needle shape is the martensite phase, right? And if we do slow cooling, if we do slow cooling, we will have perlite. Okay, we will have perlite and ferrite. So low carbon steel, if you compare just now, low carbon steel mostly is ferrite. Now we have more carbon. So this small ferrite, okay, it can be larger, okay, because we have more carbon. So we have more area of perlite. And the application, as mentioned just now, we have the hardenability. Okay, we have the martensite phase could be produced or formed at the surface, and due to this, all these application mentioned here, railway tracks, train wheel, crankshaft, gears, machinery parts, it involve friction. Yeah, and when it involves friction, it can be worn. So it need uh, high wear resistant material. So just nice for medium carbon steel because the surface could be heat treated to martensite, and when it's hard, it has high wear resistant, and at the same time, the surface, or we call it shell, the hardened surface, the shell is hard, and on the inside, we maintain the ductility, or we call it core, the core. The core is remain ductile. So this structure, it is uh, hard on the outside, soft on the inside, or ductile on the inside. So it uh, against the friction, it is good, and also it does not expose to brittle fracture because we have sufficient ductility. So okay, so that is all about the plain and sorry, heat treatable. So we have mentioned that. And high carbon steel. Okay, we plain high carbon steel. So high carbon steel, the composition 0.6 to 1.4. So let us sort it down. 6 to 1.4, right? And right, due to high carbon content, they can be heat treated by quenching. So has no problem for this one to be to form the martensite. Okay, they're almost always used in a hardened and tempered condition. So tempered, we harden it. We form the martensite, and then we expose to educate temperature, so it regain back some of the ductility to be uh, used on to be applied. Okay, and so how this is how it looks like. Uh, we have perlite and pro-eutectite cementites. Okay, perlite. I think you guys already familiar with this term, the alternating lamellar structure of ferrite and cementite. And apart from that, if we recall back the what you call the phase diagram, the phase diagram. So you have this eutectite point and eutectite temperature. So if we go, and this is actually for steel is around point, I think 8.8 or 0.77, 0.77%. So if you have higher amount of carbon, so you will be in this range, and due to this, range, this this is eutectite temperature. I hope you could imagine this situation in the phase diagram. So this is austenite here. So we have austenite plus cementite. Austenite plus cementite here. So we have this formation of cementite, and it occurs before the eutectite temperature or higher than the eutectite temperature. This is what we call the pro-eutectite cementite. Okay. So the microstructure, it have perlite. Okay, perlite like this one. You can see the lamella, and also at the same time it have this cementite, pro-eutectite cementite. And if we quench it, okay, if we quench, you will have this martensite of needle shape. And I think this one we tempered already, this microstructure. So you have less amount of the needle shape. Okay, if we zoom in, you can see. Okay, so right. Application of plain high carbon steel is that because it is strong, but the ductility we lost a bit, so we can use them as a string wire form. For example, in this one, Zopper, and they are especially wear resistant and capable of holding shock edges. So this is plain for plain carbon steel. Plain carbon steel. Now we add some alloying element. So when we add some alloying element like vanadium, tungsten, moly, then what we have is the formation of precipitate. Okay, like usual, you add alloying element, exceed limit solid solubility, it form the precipitate. Okay, and especially for tungsten, because this is steel, you automatically inside you have the carbon, and furthermore you have very high amount of carbon because this is high carbon steel. So it form carbide with tungsten, and tungsten carbide is very hard and used as a tool in tooling, as a tool, as a material for tooling, and this makes the steel as tool steel. Okay, tool steel. Okay, our time already passed, but allow me just 1 or 2 minutes more. Okay, sorry, because this plane is done and this tool is now we are looking at. So we just finish off at the tool steel. So it formed the tungsten carbide, which is very hard, very wear resistant, so it can be used as the material to be used as tool. For example, this knife, razor, hacksaw, it need to be high wear resistant. Otherwise, you use the you use the hacksaw and then suddenly all the steel gone, so you cannot use. So you need to be wear resistant to maintain the sharpness and so on, right? And if you add, okay, if you add, this is the final one, the the effect of alloying we will continue in the next class. So if we add a combination of moly, tungsten, and vanadium, more than 7%, okay, and we have more than 0.6, we have HSS, high speed steel. So it is tool steel, it's almost the same, but it has heat resistant. So if you machine, you use as the machining tool, you don't want to keep all those heat. If you overheat, then it might give effect on your material or the the the, the tool itself. So by adding this alloying element, we have HSS, high speed steel, and the main difference is it has heat resistance and durability. Right. So that is all for today. Thank you for participating in the lecture. I hope you guys could understand all this part. Okay, girl. You guys still with me?
Yes, doctor.
Yes, doctor.
Okay, okay. So boleh faham? If you don't understand, please ask. WhatsApp also can, no problem. All right.